Welcome to problem 8. It's 6:30 p.m. So let's see how much I can do before I need to start cooking. Show that the map z maps to the square root minus 1 times z gives an analytic automorphism of the additive group. Isn't that trivial in view of the introduction? So we need to show that it's a Lie group, a 2D Lie group, so analyticity is obvious, I think. So we need to show that f of a plus b equals f of a plus f and b. And that's actually easier to check on C. And then we need to check that the lattice is mapped to the lattice. So that the projection, but this problem made me think, what are the automorphisms of this group? That's a totally new concept for me. So I thought a little about it, and let's see if I have found the answer. So we have the projection. And then let's have an automorphism. There we go. Together with P, we get a map from C to CL. Phi of the projection now C itself, or R squared, is simply connected, so this may be lifted to a map. Now let's call it what should we call it, F. A map F tilde of C into C. So the projection, so that F equals F tilde and then the projection. So which maps do we have of this kind? So the lattice has to be mapped onto the lattice. And I believe that has to be a linear map. So it's defined by a matrix, and it has to be, to get the lattice mapped to the lattice, we need to have integer coefficients. So that means that F tilde must belong to GL2 of Z. Now it has to be, it has to have an inverse, so it must have determinant 1 or minus 1 to be able to have an inverse. I guess that's GL2 of Z. So I think that that's the automorphism group. And then when we choose an element here, for instance, write that we turn 90 degrees clockwise. It has determinant 1. Then the lattice is mapped to the lattice, has an inverse, so that every lattice is covered. So I believe that's the point here. Now, we should show that any Gaussian gives an endomorphism. And this is just a distributive law on C. And then the fact that a lattice is mapped to a lattice again follows from the remark up here. So that was A, with my own little idea, or what shall we call it, result on the automorphism group. If B vanishes, then the map gives, by looking at the definition, show that the map gives an automorphism on the elliptic curve. So we have to find formulas here for the Weierstrass elliptic function for Iz. We have already noticed that this should give minus the same guy. And this one I'm really not sure what we get here. But I'll do this a little more thorough, because what I want to show is that in this case where we have G3 vanishes, then all coefficients G4n plus 2 vanishes. We haven't done this before, though it has been between the lines. I've never thought about it. So, to do that, we have to... I've mislaid the book. We have to look at this series expansion. On page 23. So I'll try to do this by induction. We already have that G3 vanishes. So that's, of course, n equals 1 we get there. So a higher guy in the expansion of the Weierstrass Z function. They occur with set to the order 4n. So G6 comes to set to the 4th. So I want to show they all vanish. So we have some time. I think I'll do it on the next page. So it's G4n plus 2. I'll show vanish by induction. And we already know that G6 vanishes. And they occur in set in 4nth. And it's the differential equation Why do I write these sets? Well, never mind. So we have a power series expansion. Etc. And in the derivative, I will check where it comes the first time. So we take a specific 4n plus 2 and look where does that occur the first time. Oh, I need the derivative as well then. Now, what was that? There we go. So we get all the odd powers. So let's check where we get set to 4n. They are all odd. So we have to get to, there's of course set to minus third. And that's the first time it occurs. Yeah, we need to check a guy here, where does it occur first? So G6 occurs first in the double product. So it comes as a constant. And the next G10 will come with set to the 7th, so that'll give set to the 4th. So I think we should be very explicit here and see G4n plus 2. That occurs in this number, 4n plus 2 minus 6. 2 down here, and then another one here, and then divided by set to the 3rd. Right. That's the first time this guy occurs. And then we need to check the other coefficients to this guy, and they are odd, so it has to be divisible by 4, and that means that it will be like 1 modulus 4 plus 3 modulus 4. So G4n plus 2, a smaller one, has to occur. So that ultimately we will have plus constant times D3, which vanishes, of course. So, now I have to keep it clear what I'm thinking. I'm thinking that the other coefficients, smaller ones, vanish, so it occurs alone by induction. So that was this guy. Then we have the elliptic Weierstrass function itself. And it's obvious that when 4 divides the power, the coefficient we get is 4n minus 2 only. So with nothing, and then the elliptic function to the third. It may be one of these guys to the third power, but 4, then 4 will always divide it. So if you put this to the fourth, then we get to the third, then we get c to the sixth. Oh yeah. The power is 3 times. So the only power is 4n plus 2, so it's 2 modulus 4 occur. So it's 3 times 2 modulus 4, which of course gives 2. So that doesn't contribute. Then we have the terms 1 product squared times another one. The guy we square gives an order 4, so the other one has to be 2 modulus 4, so that vanishes as well. And the third possibility, that we have a product of 3. If 1 is a factor of 4, multiple of 4, then g, one of the smaller g, 4n plus 2 will occur, so it will vanish. So they all have to be 4n plus 2. Adding them again gives 2 modulo 4. So everything here vanishes. The power set 4n minus 4 do not occur. So that was the point here, that only powers 2 modulo 4 occur. So when we put I2, we get something I squared times the function itself, that minus the function. So now the derivative. Here we have 1 divided by Z3, Z. This one doesn't come, but Z to the fifth come. I'll just write it. So when we multiply Z by square root minus 1, the imaginative unit, here we multiply by I, here we divide by minus I, so it's the same as multiplying by I. So I claim derivative of Iz equals the derivative times I. And I really do believe that we needed to do this work to get it all quite clear. Now, what was the question? Oh, so that's exactly what I found, the result we needed, that it becomes minus x point I y. So let's take the last one. If L is a lattice, show there exists a complex number such that alpha L, show that alpha is a quadratic imaginary algebraic integer and that L contains a sublattice of finite index of the form. So now what is this? That is any lattice and it's a non-real complex number. That's very strange. So we need to show that there will be a lattice point not lying on the real axis. And I think we should assume that it's two-dimensional. So if we have omega 1 here and omega 2 here, oops, now that's actually a little complicated. So what did I have to show? That there is a non-real number, oops, so when we multiply this, it has to end in a lattice point up here. So it must be of the form n plus m omega 2 divided by omega 1. And then when we operate that on omega 2, oops. So this must line the lattice as well. This is impossible. I don't even want to spend time on that. I think this is wrongly posed. I believe it only holds for a lattice of this form. And then it holds for the imaginary unit itself. So it could be any of the numbers n times the imaginary unit. Now we could do this, of course, do this thinking, of course. So, but we don't need it if we have n times the imaginary unit. Now, what should we show about it? That it is a quadratic imaginary algebraic integer. I don't know what that means, a quadratic algebraic integer. But the last one, that L contains a sublattice of finite index of the form. Oh, so I've totally misunderstood the problem. They do mean that L is a general lattice. I have no idea how I can solve that. So let's say that was that for today. I'm back today, the 17th of April, and hopefully we'll be able to solve part C of problem 8. Last time I totally misread part C, and that's what happens when I haven't read the problem properly in advance of recording. So we have a lattice, and then it's assumed that there is a complex number which maps the lattice into itself. And then we have to show something. Now first, the lattice itself can be simplified So we don't have to have it generated by omega 1 and omega 2. We can have it generated by unity and some complex number. And that's because if we multiply the lattice by some complex number, beta, then alpha equals alpha beta L. Now what I'm going to show now, what was the point here? If we take alpha, then we use the commutative law of complex numbers. I just lost focus here. This lies in beta L, which equals L prime. So alpha will also map L prime to itself. Therefore, we can rotate it in some angle, and we can scale it with a real number, so that the lattice may be generated by unity, and then some omega, which we write u plus I nu, where nu is distinct from 0. So that's the starting point. We have such an alpha, and we have a lattice generated by unity and u plus I nu distinct from naught. And then we have our alpha with b distinct from naught, b non-vanishing, and of course alpha L is part of L. So that's what we know, and then we have to conclude something about alpha. So first of all is that alpha itself lies in the lattice, as unity does. So that means that A plus IB equals M times unity plus N So that gives us two equations. The next thing is that alpha squared lies in the lattice. Because of this. So that is a squared minus b squared plus 2iab. So that can be written r times unity plus s times u plus I nu, giving a squared minus b squared equals r plus su, and 2ab equals s times nu. And in all of this, m, n, r, and s are integers. So I need to find out what this tells us. I hope we don't have to go any further. I should believe not, though. I'm not particularly quick in the uptake. Here we know what b is, so that can be eliminated in here. So that we get n nu, and nu is distinct from naught, so we can divide by it. So that gives us 2an equals s. I need a new idea. I need a cup of coffee, so I'll just take a break. I'm back. An hour has passed. I've had my coffee, started watering my plants, and worked on this problem a little. Now, what I try in these situations is to make an example, numeric example, to see what we are dealing with. And I found two. If we have a lattice generated by 1 and 3i, then we have alpha equals 9, or 3i will do. 3 times the imaginary unit. Of course, 1 times alpha lies, and 3i times this minus 9, which is spanned by 1. So that was one example. The other one was if we take 1/3 plus the imaginary unit, then we need to take 9 times the imaginary unit. When we multiply by this, which then we multiplying this one by 9 gives 3 plus 9i, and which lies in the lattice, and this times 9i. So why couldn't we just do with 3i? That's because then we get 1 plus 3i. I don't know why we can't use 3i here. But anyway, so I got 2 examples here. So it's actually possible. In both cases, alpha is imaginary. The next idea I got was so we have alpha is written as j plus k omega. Alpha squared is written as L plus m omega. Alpha to the third is written p plus q omega. That gives some algebraic relations. And combining these two, we do get a second order equation for alpha, eliminating omega. So we get, if we multiply this by k alpha squared minus m alpha equals kl minus mj. So it's just, and k is distinct from naught. So we do get a second order equation. And doing the same with these two guys, we get a third order equation. And that means that the polynomial we get from these two will be divisible by this polynomial. The residue will vanish. That gives us some connections. That was quite intractable, and it didn't tell me anything as it were. So that's where I'm stopping today. I can feel that I'm not, I don't know why, I don't get the right ideas, so we'll just stop it, and then hopefully tomorrow I can. Good morning. It's now 8:30, April the 19th. So 2 days have gone since last recording. I found the solution to question C. First, I'll just add a note to my answer to part B. These transformation formulas, we already knew them from the work we did in paragraph 6. I just wanted to see if I could. I was sure I could derive it from the recursion functions, recursion relations for the coefficients G2n, and it turned out that I could. So that was what I wanted to do with part B. Now part C gave me some problems. First, I made some examples, and then I realized after the last recording, that any Gaussian integer would work here, and here any integer in the lattice itself, or any element of this number in this lattice itself would do the trick. So that reminded me of some number theory I did some years ago. And L here is not only a lattice, it's actually a module, a set module. So that recalled me of something in this wonderful book by Helmut Koch, Algebraic Number Theory, which starts off with a section orders in algebraic number theory. And there we have the exact, I forgot my glasses, so I'll just get those. I'm back. If we see proposition 1,1, it's not really clear. Well, we have a module M, and then if alpha M lies in M itself, then alpha is an algebraic integer. And we'll just prove it. That's not my proof. I'll just rephrase the proof in our setting. So we have alpha omega 1 can be written a 1,1 omega 1 plus 1,2 omega, where the a's are integers. And that means that we have a relation a non-trivial relation. That means the determinant of, I forgot the, now minus alpha here. That means the determinant of this matrix vanishes, and that gives us a second order equation for alpha, which means that alpha, and these are the coefficient alpha are all integers. So it means it's not only a quadratic extension of the rational numbers, it's actually an integer in some quadratic extension of the rational numbers. And then, of course, if we are lattice in the complex plane, then it must have somehow involve the square root of a negative number. So that was the solution to problem C, and I must admit that I did not get any credit for solving this problem. So I found it in this book that I've read. The good thing about this book is that you find much material that you can't find anywhere else. So I can recommend it.